Now we are going to define a path when we move between several strategy profiles and only one player moves. And of course, that is irrelevant to the definition of potential, and that's also related to the definition of Nash equilibrium. And eventually, we are going to arrive at a characterization of a potential which is a bit similar to this idea of closed path on which the changes are totally zero in physics. So this is a bit similar to this physical idea. So a path in our sense for us is a sequence, the strategy S at time 0, at time 1, and so on. Potentially it can be unbounded, indefinite. Potentially it can be indefinitely long. So for any time t greater than or equal to 0, there exists a player such that there exists Si prime strategy of that player, which is not the same as the player strategy that player strategy was in time t minus 1. And the time t, that player plays that strategy, so that player deviates from what was in t minus 1, while the other players, and I should have written t minus 1, the other players keep doing what they used to do. And of course, I need to change some typo, fix some typo here. Because at time t, that player I, so there is one player who changes, the rest do the same what they did in time t minus 1, of course, not at time 0. So exactly one player changes her strategy. Player I, there is some I such that player I changes from Si to Si prime, and the rest do what they did in the previous time. So that's what it means path. Exactly one player changes strategy. We call the strategy profile at time 0 the initial point, and if the path is finite, so if there is also the last profile, then we call it the terminal point. So let's just look at two examples. One example is a path, because at the first change you have the second player who changes from B to B prime, and then the first player changes from A to A prime. Exactly one player changes. The second illustration, however, is not a path, because indeed at the first step the second player changes from B to B prime, but at the second step we have two player changes. First, the first player changes to A prime, and the second player changes back to B. So we have two player changing at the same time, and that's not a path according to our definition. Okay, so we have defined the path, and as I said, it's very much related to the definition of potential, and that's going to be therefore natural to talk about potentials, paths, what it means, how we can characterize potentials with paths, and so on. Now let us look at several other definitions. So first of all, there are, by the way, definitions which are very, very famous. It's all this classical. This course is all classical, but this definition are especially known. So a path, as I said, it's just a recapitulation, is a sequence such that exactly one player changes his strategy at each time. As the second definition is that a path is called an improvement path with respect to a game. It depends on the utilities. If at each time the utility of the change in player strictly increases. Please notice we look at the utility of the unique player which changed her strategy. We do not care what happens to other players. And the third definition, a game has a finite improvement property, FIP in short, if every improvement path is finite. So we cannot improve till infinity. Because in some games, you don't have this. In some games, let us go back to the example of the match in pennies. Here we don't have the finite improvement property because, for example, basically the cycle, which we demonstrate in the proof, has this property that each player who deviates strictly increases her own utility. That's not, so there is an improvement path which is infinite because we can make those cycles infinitely many times, and therefore this game does not have the finite improvement property. Of course, I'm not talking about infinite paths in the sense of finite path in the sense of the number of strategy profiles they have in general, because that game matching pennies, for example, has only a finite number of strategy profiles. So, of course, in that sense, every path is finite. But we are talking about the possible length of path when it's allowed to get back to the same state. So, okay, this path is a myopic process, and having a finite improvement property means that these processes will stall after a finite number of times. We cannot improve in that way indefinitely. So we have defined the path. We've said what it means to have an improvement path. And we've said what is that a game has the finite improvement property. A nice lemma, which is interesting for its own right. In a finite game, having a generalized ordinal potential, so the largest class of potentials, is equivalent to having a finite improvement property. So it's like if you have the finite improvement property, it's equivalent to having this generalized ordinal potential. In particular, please recall that this match in pennies does not have the generalized ordinal potential game. So it's already not surprising, therefore, that we also saw that it does not have the finite improvement property. Now the proof is the follows. If a game, by the way, I just need to say that this proof, as most, pretty much all this lecture, I should have said this, yes, is built by the classical paper of Shapley, Monderer and Shapley. And Shapley was a Nobel Prize laureate, so he was definitely a very famous scientist, and also Monderer is quite a famous scientist. So those two people wrote a very classical paper called Potential Games in '96. So the notion of potential game itself, I think I can trace it at least to Rosenthal from the 70s. And I think Rosenthal proved that each congestion games, which we will define later, is a potential game, and that's how he also, I think, proved that it has a Nash equilibrium. Because as we have seen, a finite game, which is a potential game, has Nash equilibrium. But the other direction was already done later, 20 years later or something, by Monderer and Shapley. And in general, this paper, including that current proof, which I am going to present, of this lemma, is according to the paper. Of course, not exactly. I add some things I've thought about, like the examples. Some of them are there, some are mine. But the bulk of definitely of this lecture is according to their paper. So the proof is as follows. If the game has the general ordinal potential P, consider any improvement path S0, S1, all those. So S is a vector in the sense that it's a strategy profile. It has several strategies. Now, since it's an improvement path, the deviating player strictly improves her utility. And therefore, the definition of a general ordinal potential means that the potential strictly increases. Now, since the game is finite, then the path has to eventually cycle on itself. And since the potential strictly increases, it cannot come back to itself. Now, since the game is finite, it means that the path is finite. So, this path has to be finite. Now, conversely, assume that the game has a finite improvement path. And we need to prove that it possesses a general ordinal potential. It's going to be a little bit harder, but not hard. So we need to find some way to define a general ordinal potential function. So we define the following binary relation, which has the meaning of being smaller than, and we write as smaller, s smaller than t, if they are the relation is on the profile. So strategy profile s is smaller than t if the strategy profiles are not exactly the same. So at least one agent differs. And there exists a finite improvement path from the initial point from I think I made a mistake. Yes. From S to T. That's why S is smaller than T. There exists a finite improvement path from S to T. 1 second. Okay, so I fixed it. S is smaller than T if they are different as strategy profiles. And there exists a finite improvement path from S to T. Now, the fact that we have a finite, how do we call it? Finite improvement property implies that we can never have we can never come back by concatenating such paths, because if we cycled, it would allow us to indefinitely long improve along the cycle, and therefore such a concatenation is still gives us that the start of the first path is smaller than the end of the second path, because we don't come back. So this is a transitive relation. And having defined this transitive relation, it's enough for us to represent the strategy profiles in the following sense. A subset of strategy profiles S, which are all these profiles, a subset Z is called representative if there is a function P, which would be of course the general ordinal potential, such that for each two profiles in Z, if one profile is larger than the other one, then the potential, the function P of the larger profile is also larger than the other one. So that is enough to say that it's a general ordinal potential. Now, how can we show that we can represent all the profiles? Then take a maximal represented set, so as a represented set which is not possible to, which we cannot extend. No, it is not necessarily maximum, it's maximal, please notice. And we just prove that this set has to be of the set S. Assume by contradiction is not the case. So assume by contradiction there is a profile X in S which is not in the Z, which is not represented. Okay, so let us then continue here. And now there are three cases in all of which we arrive at contradiction. If this not represented profile X is larger than all the profiles in the set Z of represented profiles, then we can extend the function P from Z to Z united with X, when we add X, by making P larger than the maximum value of P on the set Z. Remember that we assume that the game is finite, so everything is finite. We can just look at the maximum of P on the set Z. And then that is larger than everyone, so we're going to define its P as larger than everything. And it's going to be fine. It contradicts, it means the assumption that Z is maximum. It's maximal. It means that we can extend actually Z in the way in which it will be represented. So it's a contradiction. Another option, what if X is smaller than all the Z's in Z? Then we can do similarly. We can extend P to the union of Z and the set singleton which includes X by making it the smallest. So by looking at the minimum of P on Z and subtracting 1. Another option, the other only option, is that X is neither larger than everyone nor smaller. And then we have at least someone who is larger and at least someone who is smaller. Now why? That's because, let me think. 1 second. We don't actually need this. We don't need this because it's important that if we have a certain relation that X is larger than 1, then the function P, then the potential, will indeed fulfill that Px is larger than P1y. If there is no relationship between X and Y, then we don't have any obligation. So it's not even important that what if there is nobody smaller or larger. It's important that we do take care if there is someone smaller or larger. So if the set, we look at all those in Z who is smaller than X and look at the maximum which is smaller. We look at the minimum of those who are larger. And since it's transitive, we know that the maximum of those who are smaller is smaller than the minimum of those who are larger. And with proof transitivity, remember, we use the finite improvement property there. And we can just define the P function to be the arithmetic average, fulfilling all that we need. And we already can extend this representation to Z when it's extended by X. So it's a contradiction. Anyhow, we can extend this Z. So we cannot have a Z which is maximal and not all the set of profiles S. And therefore, we can represent all the profiles. So it has a generalized ordinal potential, this function P. Okay, so we have proved that for a finite game, having a generalized ordinal potential is the same as having finite improvement property. So if you cannot infinitely improve, if and only if you can just assign kind of a topological order. It's very, very kind of, but it's a good intuition. So now let us go further and make a corollary. That it's a simple corollary that if for each player and for each strategy profile S, any deviation of that player to another profile, not SI but some TI, will change that player's utility. So a player cannot deviate and retain the same utility. And the game possesses the finite improvement property. Then the game has an ordinal potential. Okay, the proof is simple. The finite improvement property, which we assume, implies, by the lemma we have just proven, that the game has a generalized ordinal potential. Now, the fact that you can never change your strategy, be the only one who changes the strategy, and retain the same utility, means that each generalized ordinal potential is also an ordinal potential. Because an ordinal potential can differ only if you retain the same utility, but the potential then may change, does not have to be the same in a generalized ordinal. So in this case, this condition means that this generalized ordinal potential has to actually be just an ordinal potential, as we see, as we state. Now let us go back to the definition of a generalized ordinal potential to say that, to see again that this definition implies that it has to be ordinal potential. These are all quite natural definitions, but you may not recall them right now. So the difference from the definition of ordinal potential is that if the utilities of a player are the same after the player deviates, then we don't have any condition on the potential. But that assumption that we had in that corollary is that exactly that if you are the only one to deviate, your utility does not stay the same. And therefore, you cannot fall into this case, which can actually be the difference between generalized ordinal potential and just an ordinal potential. Okay, so let's go back. And an interesting question is the potential function unique? Well, there may be, it's clearly not unique up to a constant. It's not unique up to a constant because we only look at the differences of this function. So we can always change all the function by a constant. But is the potential function unique besides it? Well, no. There may be many weighted potentials, and therefore also many ordinal and generalized ordinal potentials, because those are even looser. But if we have an exact potential, then indeed those are unique. So even two exact potentials for a game, there is a constant such that those potentials are equivalent up to this constant. Okay, and the proof is quite simple. So we fix any profile and define a function from the set of profiles to real numbers with in the following manner. The function h we define is a sum over I when I goes from 1 to n, the number of players, of what is the utility that player I gains, or what is the utility delta, it can be positive or negative, when the profile changes from AI to AI minus 1. So we begin actually with from A2 to A0, from A1 to A0, from A2 to A1, and so on. A0 is S. The point here is a profile at which H is defined. And AI is what AI minus 1 was besides player I, who in this case plays what she does in strategy Z. So AN would be like completely strategy Z. And basically if you look at A0 and it's only S, and then we gradually move to Z. And we look at the utilities at those points. Now, since we assume that both P and Q are execpotentials, then the utility of I at AI minus 1 minus the utility of I at AI is equal to the difference of the execpotentials in those points, and that's a telescopic sum, so that we have cancellation, and eventually we have only the last one minus the first one. So H of S is the difference of the potential in S minus the potential in Z. It's true for each potential function, in particular, so it's true for P, and it's true for Q. Therefore, P in S is equal to H in S plus PZ, and H in S is equal to H in S plus QZ. So the difference is only what happens in point Z. Now, since Z is a fixed point, does not depend on S, we have proven that P and Q are equal up to this constant, and the constant is something which does not depend on S, on the point in which we evaluate those functions. So we prove that two exact potentials, they would be the same up to a constant. So the exact potentials are unique up to a constant. And finally, we arrived at a physical characterization of an exact potential game. So a characterization which resembles this idea of going over a path which we have in physics. For this, we need first to add some definitions. So we define what it means to have a path, and I remind you that it means that you have profiles such that each next profile differs from the previous one by exactly one player strategy. So exactly one player changes her strategy. Now, given a finite path and a vector of n functions, for example, utility functions of the players, but it can be any n functions by now. Each function is from the set of profiles to R. Define I, so a function of this path and of the function vector, to be the sum of the differences of the values of the functions or on the points of the path. So sum goes, k goes from 1 to the number of players. We look at the points as k minus 1 in this path. And the functions we are talking about are given to us, but we look at function ik each time, and ik is the only deviating player, or when we move from sk minus 1 to sk. There is exactly one deviating player because it's a path. So the player who deviates, we call him as ik. And we look at vik. Now, a finite path is called closed if its original point is equal to its finite point. A finite closed path is called simple if only the original and the finite point coincide and all the rest of the points are different. So Sk is different from Sl. If K and L are any two different indices besides the first and the last, so we look only at the indices till n minus 1. And the length of a simple closed path is the number of its distinct vertices. So in the case of S0 till Sn, it's n, because the number of distinct vertices is exactly n. Now, having given those definitions, we look, again, remember what I means, the sum of those differences of these functions. We give the following characterization, which is really physics-like. It's really similar to physics. So, given a game in the strategic in the strategic form, the following statements are equivalent. First is that G is a potential game, an exact potential. Second is the I of any finite closed path gamma n and the utility vector, I should have written here the utility vector, is 0. Third, the I of any finite simple closed path gamma and the utility vector is 0. And fourth, then for every finite simple closed path gamma of length 4, the utility vector is 0. So all those four statements are equivalent. So of course, if we know that at least one of them is true, it's reasonable to use either that it's a potential game, or the strongest of the other statements is that I of gamma and utility vector is 0 for any finite closed path. But if you want to prove that at least one that those statements are true, then we can use the easiest to prove fourth statement. That it's enough to prove that for every simple closed path gamma of length 4, the I of gamma and the utility vector is 0, and that will be enough to prove that each one of those statements